Hello, everyone, and welcome back to Stat385. We are going to continue our conversations on vectors. In particular, in this video, we'll discuss the basics of generic vectors. Last week, we covered atomic vectors in a lot of detail, and discussed types of objects, types of vectors of objects of certain types within a particular vector, and how sort of type coercion worked, and we discussed some length coercion and stuff like that. So this time we're going to discuss generic vectors. Okay, so let's see here. I have my RStudio open. I'm inside my Stat385 R project. I need a new script. Okay, so again, so just a little refresher. We did stuff like this last time, where we used the C function to combine atomic elements of the same type. A string, more text. Okay, and so we can show those objects and whatnot, and use the C function to combine those things together. And we demonstrated different sorts of how to display the types of these objects. Okay. Okay. So now we're going to discuss generic vectors, which are most often called lists. So like vectors, like atomic vectors, they're going to be a collection of elements, but these collections of elements can store objects of differing types. So let's just demonstrate. So remember last time, if we were to do something like this, where we had elements of different types, then there is some coercion. So like true gets converted to type double, or maybe type integer in this case. And then I just want to do this real quick. 0. Okay. Easy enough. 3.2. And then, and in this case, we have a character vector, so everything's going to get converted to character. So now let's introduce a list. Okay. So instead of using the C function, we're using the list function. And this is going to do something a little bit different. Okay. So here, so I'm hitting Command Return on my Mac to display it again. Okay, so here we have the first element of this list is an atomic element of type integer. Then the next one is an atomic element of type logical, and atomic element of type character. So now the list returns these three separate objects in a slightly different print syntax. So here we have the first element of the list, second element of the list, third element of the list. And in this case, these elements are just atomic vectors of length 1, and that's what's getting printed out here. So we could consider a more complicated structure if we like this to just be, not too complicated. Okay. Actually, let's keep everything intact so you can see it. Okay, so now let me get my vector, my atomic vector here, and let me get my string, or my character vector, and let's just do different lines for the elements. Okay, so perhaps a little bit more interesting, we can have, so it's still a list with three elements. In this case, the first element is now an atomic vector. Second element is an atomic vector of numbers, and then we have an atomic vector of logical values, which is just the single element, and then an atomic vector of an atomic character vectors, the third element. Okay. So one thing to note here is that in each of these cases, in each of these list cases, the type of the object returned is an object of type list. So in this case, this is it supersedes all of the types of the elements, and we have an object of type list here. Okay, So, yeah, so here, of course, the elements have no singular type, and type list supersedes the type of each one of the elements. In this case, the elements being atomic vectors of different things. Okay. So just to go back to our combine function again, so we introduced the combine function, C, as a way to combine different atomic elements together. And if we respected the same type, it would create a vector of that particular type. Of course, there's also the type conversion that we saw before. But the C function works more generically than that. So for instance, we could have an element 1. Actually, let's do list 1 and an element 1 together. And then this combine function here is going to combine them into a list. Okay. So, yeah, so then we can see that C functions, or the C function is more generic than just something that combines atomic elements together. It can also combine lists together. Let's see what happens when we take our more complicated list. So we have a list of one object and a bigger list. And so here it's just stringing together the different lists. Okay, combining them together. So now, right, our list with our atomic vector in the first element, since we've combined it to, since we listed our list with just one element first, now that just gets, the index changes from 1 to 2. It's now the second element of this combined list. Okay, great. Okay, so going back a little bit, we can see that, let's take our list here, and then let's give it a name. So now we're going to assign our list the name foo. It's going to appear in our global environment. And if we print foo, we can see the list that we just made. And here, note that, when we had the print statements earlier, there's this 1 to index the first element. Here, there's now this double bracket notation. And we'll get more into this when we cover subsetting in the next video. But we can see that we can pull elements of this list directly out by using this double bracket notation. Okay, so... and then more interestingly, if we have, say, this list, okay, you can see it's going to be added to our global environment. All right. So we can see that the second element of this list is that atomic vector. Okay. Now, not to get confused with the subsetting that we'll see later, but if we're just kind of introducing some of this now. And if we use the single bracket notation, which we will use to pull elements from a vector, and we'll get into this in more detail, but we can say that we can use it here to demonstrate that what this is doing is pulling the second element directly out. So, okay, so in foo, that's the element true. In bar, okay, it's pulling the atomic vector out. Okay, so similar to what we saw in vectors, we can create named lists. So let's take our simple one here, and we can say I want to give everything a name, just like before. Okay, and then now instead of having that double bracket notation, we have the elements which are themselves named. Okay, so this is very useful because I'm gonna just overwrite foo. Okay, and then because now if we know the names of this list, we can call the elements directly. Okay, cool. So that actually comes in handy quite a bit in R programming. So, for instance, when you fit linear models in R, this being a statistical language, it has functionality to fit linear models. what's actually getting returned here is so you would provide linear model, formula, data set, and then there's all kinds of other arguments for this function. And then what gets stored is a list of a particular class, which we'll get into later, but it has all of this interesting stuff. And these are named elements in a list. That's how it actually functions. So like you can pull the regression coefficient estimates directly by just calling object name $coefficient. So here it's just object name foo $c to pull this element. But you can see where this gets incredibly useful if you know what you're doing when you're using R to like fit statistical models, for instance. Okay, it's perhaps getting way far ahead of the game, but I was just trying to provide a case where you can see where these lists are extremely useful. So we've covered atomic vectors. Now we're covering generic vectors, and you can see how these things are useful. And I'm just trying to tie it to something that is important to like statistics itself, so that you can see that as we're developing the language or our understanding of this language, that you can see where it will be useful in the future. Okay, so now I'm going to pull some handy dandy text that I have available, overriding what I've done before. Okay, so I have different lists here. Okay, and in bar, again, is a named list with elements of different with atomic elements of different types and different lengths. So here we can see that in this more complicated list, we have A refers to the atomic vector of the elements from 1 to 10, or the numbers from 1 to 10, B being this one particular string, and then C, interesting, we can store a function, which is just an object itself, inside of a list. And D, which is a list. So lists are fairly general in what they can store. So they can store all kinds of different objects. On that linear models thing that I was talking about earlier, lists can store linear models. Sometimes it's useful to fit a whole bunch of things, store them all as a list, and then write a function to pull particular models out. Now that's getting really far ahead. But it's just demonstrating that like this is very useful and it's very general, and that's why it's a generic type vector as opposed to atomic, which is the one particular element. Okay. So yeah. So so these two things that I've stored, foo is a list, bar is a list, and baz is a vector, and so we can test whether or not what these things are. If we ever get confused. Okay, is not vector, bar, baz, okay. Okay, so everything here is a vector. Recall that a list itself is a vector. It's just a generic type vector containing elements of different types, possibly. So now, a list is a generic vector, but now if we try to differentiate between atomic and generic, then now we'll start to see differences. Okay. So our lists are not atomic vectors, and our vector is. Even if we were to overwrite this and contain some text here, so store it. So if you can see what's going to happen if you followed what happened in the global environment. And when I run this, I still get false, false, true. So by changing one of these objects to type character, that's just going to, through coercion, is going to change the whole vector to character so that it is in fact an atomic vector. Okay. Just a refresher. And lastly, we have functionality to determine if an object is of type list. And I think we can see where this is going to go. Okay. So first, the listings are lists, in fact, and the vector is not. Okay, so one more little thing here. The length function. Oops. Okay, so we can see what the lengths of all of these different objects are. So why don't you try to guess what the lengths will be for the list objects? Okay, now I'm gonna run it. And is this what you guessed? So 3 was, for foo, was probably pretty easy. So 4 may be the tricky one. So here, what it's doing is it's again, the length is going to return the number of elements inside of one of these particular objects. And here, it's not going to enumerate all of the components of the list itself. There's 4 elements in this list, and then those elements may contain, more than one particular object. So here, for instance, that the object in the list is just A, and then A contains 10 numbers. But the length of the list, but for purposes of the length of the list, this is just one element. Another element, another element, another element. That's why there's length 4. Okay, so this function comes in handy quite a bit, especially when we get into data frames, which we will cover soon. So the structure function, I think it's structure, right? Pack display the structure of an arbitrary R object. Cool. Okay. See, I get confused. I need to use the help command to see what I'm doing. Okay, so the structure function will display some information about each of the objects inside of a particular structure, in this case a list. So here we have A is an integer vector with 10 elements, and it displays some first occurring objects in that list. In this case, it can enumerate all 10. B, character vector. C, a function. D, a list, and then it displays some information about the lists, or about the elements of that list as well. Okay, so there's a wealth of information inside this structure function. You could also go here and see very similar, the same output, in fact. So RStudio is very nice and friendly for us. We can also use view with a capital V. And if I run this, it's going to display information in a new panel about the object that you're choosing to view. Again, if you need more detail, you can see it here. Okay, cool. This gets very handy for data frames. Okay. And now on to data frames. So far, let's just see where we're at. So we've covered lists, a generic vector. It can house objects of many different types and many different lengths. So now, if we want to impose some additional structure, we can arrive at a data frame, which is one of the most important objects in R. So data frame houses data, a collection of vectors of, again, different types. But if you think about a statistical analysis, then you have some columns of measurements on subjects, which are usually it's for each row records information on a particular individual inside some sort of study, and then the columns display the individual values that are recorded. Those values can be, they can be different types, but most notably you have qualitative and quantitative variables that you've recorded on individuals. So right there you're talking about characters for qualitative, and numbers probably double for quantitative variables. So if we were to now restrict attention to, if you have n subjects, in this case 5, then you can start talking about data frames. So now, right now, what I'm doing is I have a named list, as we've seen before, with A, B, C, D, and then each of these has 5 elements, and we can show that this would be a data frame. Right now, it isn't. It's just a list with 5 elements. So right now, you would say if this is a data frame, you would say that I'm crazy. It's just a list. Now, I can just change one thing here. Instead of using list, data dot frame. Okay, so it's a slightly different thing than a list, right? I changed the name, but you can see that I'm using the exact same elements or object names and objects themselves. All I did was just change from list to data frame, and we get some different output here. So what happened? So above we had separate objects with names. Now we have it all sort of fused together. So I have my A, which is my numbers going from 5 to 1, B, which is A 5 times, C is this following logical vector, and D is just a bunch of ones. So here we can see that, okay, so if this would be, something that I wanted to analyze, I have 5 subjects, and you can see the 1, 2, 3, 4, 5, which is not a part of it, but it indexes the row numbers for you. And then I have 4 variables that I've collected on these 5 subjects, one being type numeric, or in this case integer, and then I have a character vector, a logical vector, another numeric vector type integer. Okay, so cool. And we can give it a name just as before. Again, this is something that if you're performing actual analysis, either it's a throwaway data set and you can give it a name like this, or I often use DAT, so I'm going to just use DAT for this. Okay, so now I can take my data frame and I can assign it the name DAT. Okay, and then if I use structure, again, I can see some detail about the elements inside of this data frame, right? Of course, I could go up here, do roughly the same thing. I can view it. Now the viewer is going to be a little bit more interesting because it's in this more tabular format. Okay, and then what else did I want to say? Yeah, type of DAT. It's a list, right? Okay, so the way to think about what this data frame is it's a list with constraints. So here again, our data frame allows us to combine together objects of different types, right? We have, numerics, and we have logical and character and everything like that. And provided that each one of these objects has the same length, then we can convert it into a data frame. Okay, and so when you're thinking about data frames in statistics or statistical analyses, you're thinking about data collected on individuals, and however many individuals you have will form the number of rows. Okay, very, very, very cool, very powerful stuff. Okay. And not like this doesn't get used too often, or I don't use it too often, I should say, but we can see some additional information on the data set. So we have names of the columns, class, which we'll get into later, and then row names. Cool. Okay, and then if we ever want to, we can pull out column names and row names directly. This does actually come in handy quite a bit, especially column names, changing things around or giving things more descriptive names, something that can happen all the time. Okay, so we already saw that the data frame itself is a list, and it also is data frame. So data frame is a particular type of list. It's very, very, very useful. And so it's given its own little designation as well within R. Okay, so one little tidbit, because I see this, people will use the name DF for data frame. It's not a very descriptive name. Neither is DAT, I guess. But for my notation, dat is something I use when a data frame isn't something that's going to be used in an analysis that I'm displaying to people. So like a throwaway name. People use df as a throwaway name. However, df is, it's not reserved, right? You can still name something data frame, but there is, but df is already used within R. It's the density function of an F distribution. So it's just, you can cause issues for yourself by mixing up this with a data frame. And so, if you got confused and you did something like this, you get this error message here. And this occurs all the time. We're not going to get into object of type closure here, but it's a message that occurs all the time. So better to use a name which itself isn't actually used in R, which in this case I use dat. Okay. Or you could use what David Dalpiaz uses, or you could just use our familiar throwaway names. All right. Okay, continuing on. Okay, so we have our data frame dat. 4 variables collected on 5 subjects. So we have commands to, if we forget the number of rows or the number of columns, we could use that. And length. Okay, so what happened here? So remember, a data frame is a list first and foremost, and the list contains objects of different types. In this case, the objects are the columns, what's measured on an individual. Okay, and if you want complete information on the dimensions, we can just get it here. So we have 5 rows and 4 columns in this data frame. Okay. So continuing on. Okay, so let's just see. We also get, since it's a list, we can extract the objects using the $sign notation. And very similarly. Okay, so again, this is very useful here. Because if we have a data set with a meaningful name and a variable name or a measurement on a subject with a meaningful name, then we can just extract the elements in a meaningful way rather than having to remember where that element or where that variable occurs in the data set. So if I wanted element D, which is just these values 1, then if I wanted to recall that, I need the name, I can get it, rather than having to, remember the number. Okay, so great. So this is a good introduction into generic vectors, and the next lecture we'll discuss subsetting and get into more detail into generic vectors. So remember, before last week we covered vectors of the same type, atomic vectors, and discussed coercion and all that kind of stuff. And now we're discovering vectors of mixed types, generic vectors, which are lists in this case. And then we covered a particular list, which is very useful in statistical analysis, or just very useful in general, which is this data frame. And the constraint there being that all of the elements of the list have the same number of elements in them. So here, again, A is numeric with 5 elements, and B is character with 5 elements, but we're constraining the lengths to be the same. All right, so thank you for your attention. Thank you for watching the video, and I will see you next time. All right, bye.